Good afternoon, everyone, and welcome to the first virtual environmental committee lunch and learn. My name is Ariane Sauter. I'm the chair of the CA Environmental Committee. Today's lunch and learn topics is engineering strategy to improve environmental and economic outcomes from in-stream construction-induced suspended sediment. Today's presentation is presented by Greg Cortis. Greg Cortis is a water resource engineer that specialized in river engineering, eco-hydraulics, and fish habitat compensation. He is working on a PhD in civil engineering from the University of British Columbia, Okanagan campus in Kelowna, where he is studying the management of suspended sediment releases derived from river construction activities. Greg is currently helping the City of Calgary and other groups to develop better practices to improve both economic and environmental outcome from in-stream construction activities. Greg's presentation will take about 40 minutes and will be followed by a Q&A. If you have any questions, feel free to put your question on the Q&A tab. Greg, the floor is yours now.
Thank you. Let's see, so I need to share my screen here, get the presentation up. All right. So, okay, so thanks for everyone that's attending. And I just want to thank the Consulting Engineers of Alberta for inviting me to talk about my research and how we might improve some of our practices related to river engineering. So I find that after I've studied this topic for a few years on top of my consulting experience, that there is a lack of understanding that leads to some practices that could definitely use some improvement, and I'm hoping that I might be able to shed some light on that through this talk and propose a few improvements that we might be able to make. So my experience that kind of led to this research started in my master's, where I was fortunate to work with some great ecology grad students on evaluating some fish habitat compensation projects, and that gave me a interesting perspective on this sort of interface between engineering and ecosystems that isn't well understood, and that's something sort of at the forefront of this issue around in-stream construction-induced suspended sediment. And what I found through my consulting work after that, working on flood mitigation work as a response to the 2013 Southern Alberta floods, was that there were a lot of discrepancies between the guidelines we were given for suspended sediment and how we were interacting with the rivers and the constraints for construction projects and design. So that kind of led me to pursuing a PhD to really dive into the underlying mechanisms and understanding of the whole topic, and I'm currently developing better ways that we can manage these projects. So to give some context to the whole topic, we currently spend about $200 to $300 million a year in Alberta on river-related projects, and about 10 to 20% of that is on suspended sediment control. These numbers vary year to year, and this is my best estimate based on my studies. And the kicker with all of this is there is a meta-analysis on sediment control done in 2014 that basically said that there's a lack of study, and this is remarkable given that sediment control devices are a requirement of regulators, yet the evidence to support their effectiveness is weak. So that's not to say that they're never useful. It's more a statement to be taken as we don't really understand when they're effective and when they're not effective, when they should be used, when they shouldn't be used, and there isn't really best management practices available right now. So what I'm going to go through this presentation is first, I want everyone to be on the same sort of playing field as far as what is in-stream construction-induced suspended sediment, why it's important, and why we do need to manage it. It isn't something that we can just go and release as much sediment as we want, do whatever we need in the rivers. We need to manage it. It's just how do we manage it? And then we'll get into the current framework and common management practices, what the engineering implications of the underlying exposure risk that's happening and the management practices we're forced to undertake for the projects, and this interesting dilemma and disconnect that happens as a result of the current practices. And then we'll get into some strategies as well. So first, what is suspended in-stream construction-induced suspended sediment? Well, really, it's any release that's resulting from construction activities in the wetted perimeter of a river. So here's a classic example of building out some riprap into a river. We have a point source plume, and that travels downstream and creates heightened environmental risk as a result of the suspended sediment. So what we have here is sort of typical sediment control measures. It seems like every project has a different specific type of measure that's implemented. Here we've got sort of a compound case of some lock block and silt curtain installation up here, and then just silt curtains down here where it's lower flow. What we find is that a lot of the times in heightened flows, it's challenging to get silt curtains to stay put, and they can build up block with silt after a certain amount of time, and they're not a perfect solution. And this is a great photo, the aerial photo here showing we had a sort of a pilot project done on the Bow River a few years ago where we were doing some experimental activities in the bow to better understand this, and it's clear by this photo that the sediment control measure was catching sediment, but a lot of it was still going downstream. So this is to say that these measures aren't perfect, and I think anyone that's been involved with these projects would agree that there isn't a perfect solution. And on the right here, we've got some classic concrete lock blocks that are being put in the river, and those are used usually when there's higher velocities. We need something with a little more structure, and this was part of a sort of an experimental activity to compare isolated and non-isolated activities. So the overall risk that we have is that we have a concentration, we have a duration, and we have sort of an area that's exposed in. And for our purposes, we can mostly manage concentration and duration. The mixing of the plume is going to be somewhat specific to the site. So we're going to, in this talk, deal mostly with concentration and duration. And here's a definition sketch of what's going on here. So we have a footprint here that activities are taking place in, that releases sediment, and the exposure risk from that plume is going to be a function of the concentration, the duration, and the location that we're interested in evaluating that risk. So we usually have one or more locations where we're monitoring, and the prescribed exposure limits or compliance guidelines are going to be evaluated at that one or more points downstream. So generally what we do is we implement sediment control measures around the activities, and this will hopefully reduce concentration. However, it comes at a cost of increasing the scope of work, increasing the release duration. So we have to ask the question, under what circumstances is this appropriate? And that's fundamental to my my research is trying to answer that question. But given our current understanding, we can actually evaluate many different ways that we can go about constructing these projects without all of the research that I'm currently doing. So ultimately, what we're faced with is we can't actually directly measure our impacts with these projects. It's just not possible. We would need to measure the effects on each individual fish that are exposed to our plume. That's an impossible task. We don't know how many fish are going to be in the given area, and even measuring that would probably cause impacts on the fish. So what we're needing to do is choose acceptable exposure risk limits to be confident that we're not going to have harm to fish. And yeah, as I said, my research is going to help to better inform this type of stuff. So how do we actually quantify our risk is the question that we're going to look at now. So how do we currently do that, and what framework do we work under to ensure we don't have harm? Now, this is something that there's a lot of frustration that I've found, not just from existing consultants or contractors, but also in the regulatory agencies. I've talked to many people that there's a lot of frustration, and it doesn't seem to fit the activities, but we don't have anything better. So I found that most people have difficulty articulating why it's frustrating, and that's something that I'm hoping to be able to shed some light on through this presentation and propose some solutions to that. So currently, we rely on the Canadian Council of Ministers of the Environment, their water quality guidelines for the protection of aquatic life. So that's generally what regulatory frameworks lean on. They suggest 25 milligrams per liter over 24 hours, or 5 milligrams over 30 days. So a short-term and a long-term guideline. Now, for projects that happen a handful of hours a day, day in, day out for a few days to a few weeks, on most cases, that's a pretty ambiguous guideline to be managing these projects on. And as a result, generally what happens is we drop the duration and have a concentration limit. And this focus on concentration results in a focus on sediment control measures without considering the other component, which is duration. And so how we usually develop the compliance is we have what are called exceedances, or we monitor for exceedances. So when our measured concentrations at our monitoring locations are above our prescribed limit, which is commonly 25 milligrams per liter above background levels, we have to halt construction, report the exceedance to the regulatory spill hotline, then try and revise our sediment control measures or practices as best we can. And the contractor, meanwhile, is standby waiting till concentrations fall and returning to background and developing a new plan. And with that comes a lot of standby costs and a lot of frustration. And that's where a lot of those comments come from, is that the process is frustrating and it doesn't seem to be very effective. So what are the engineering implications with all of this? What are our challenges? We come to an interesting ethical dilemma once you start digging into this a bit, and we have a bit of a disconnect that's at a root of a lot of these issues. So first, I just want to make a very important distinction that that an exceedance doesn't necessarily indicate an unacceptable environmental risk. One is a regulatory prescribed concept, and the other is actual risk on the ecosystem. And so when we've done everything possible or everything reasonable, given the scope of the project, to implement measures to prevent exceedances, how can we actually manage once we continue to exceed these prescribed limits? And the answer is, under the existing framework, there isn't a whole lot that we can do. But Fortunately, these regulatory exceedances and the prescribed limits only consider half of the equation. So we can evaluate environmental risk rather than just focusing on these exceedances. So if we take a step back and look at what the CCME guidelines are based off of, and many guidelines around the world, they cite Newcomen-Jensen and the severity of ill effects scale. And this was a study that undertook a meta-analysis of all the dose response study available to evaluate effects to fish from suspended sediment exposures. And what we have here is they scored effects on a scale from 0 to 14 and developed relationships to better understand those effects and predicting those effects. So this is a statistical model that was developed from this for adult and juvenile salmonids, which is cited quite widely in regulatory guidelines. So if we take that 25 milligram per liter over 24-hour limit, what we get is a value of minor physiological stress of about 5.4, between 5 and 6. And a lot of the guidelines, what they do is they suggest that the effects that we want to be limited to are those that are rapidly recoverable upon elimination of the exposure, is sort of the general trend with these. So let's look at what this means from an engineer's perspective. Take an engineer's eye to this equation and the relationships here. So first off, it's easy to see that we have an intercept and two slope terms, and so we predict exposure risk or severity of effects from the natural logarithm of duration and concentration. So that's an order of magnitude analysis of this is generally what that implies. So the greatest rate of change of effects are going to occur at low concentrations and durations. And importantly, concentration alone is a poor predictor of effects, and that's cited or that's stated in many suspended sediment effect publications. So an interesting thing is this actually contradicts a lot of traditional engineering theory. In particular, this idea that if you have a industrial or wastewater effluent into a clear system, you want to mix it as efficiently as possible to reduce concentrations. Well, mixing efficiently exposes more habitat to the pollutant, and if you are exposing more habitat to sort of an incremental change at low exposures, what you're doing is you're creating a higher exposure risk. So it's a bit of an oversimplification of what's going on, but it's important to note that our traditional engineering intuition or understanding of certain concepts may not apply as directly to suspended sediment as it might other types of pollutants. So another thing that might be a bit different here is that this is a statistical model, which means that we need to understand the uncertainty associated with the coefficients that are presented in it. So if we take the coefficient for duration and the coefficient for concentration, there's a lot of uncertainty around those. And so what we can say is that they're really comparable in their importance. It's not like one is 0.1 and one is 1. That would be quite a bit different, but they're very similar. So we can say that reducing duration may be as important as reducing concentration, and it may be just a factor of what we can control better given project constraints and site characteristics that may govern should we be controlling duration or should we be controlling concentration. Now, to simplify that further, we can say mathematically if those coefficients are very similar, we can actually use the product of duration and concentration as a single parameter to evaluate our risk. So if we do a simple derivation on proportionality there, we get duration times concentration, which is what we refer to as dose in units of milligram hour per liter. So if we reduce dose, we can reduce exposure risk. So that's a very important thing that we can now take one step further to tie it in a little closer to what us as engineers might be more comfortable with. And so dose has units of time times mass divided by volume. So if we take that and we multiply that by discharge, which is volume divided by time, we get mass. So mass is proportional to dose, which is proportional to exposure risk. So when we're considering suspended sediment effects in our design, we should be designing to minimize total mass of sediment released from these projects, which we'll talk about a little more once we get a little further into the presentation. But talking about the current framework, we don't really get any incentive to be reducing total suspended sediment mass under the current framework. Limiting concentration may come at a cost of increasing duration, as I mentioned previously, when we install sediment control measures. So I undertook a pilot study a couple of years ago that I mentioned previously to demonstrate this issue. And so what we did was we undertook some sort of typical stream bed disruption type construction activities within an isolation, and then we did the same thing outside of an isolation. And the results of that I've presented here, where we have a plot with average concentration on the y-axis and duration on the x-axis. And the contours correspond to equivalent risk contours from the Newcomen-Jensen exposure risk model. So, so each of those will correspond to a certain value of SEF score. And what we see is we would expect that the non-isolated case to have a higher concentration than the isolated case. And that was true. But what we also see is that the isolated case is on a higher SEV score contour, a higher exposure risk contour than the non-isolated case. And the reason for that is because all of the activities to construct that isolation caused the project to take longer to complete and ultimately release more total mass of sediment than the non-isolated case, which got in, did the work, got out, and it was a more intense exposure, but it took much less time and much less release of sediment to get that done. So we are faced, knowing this, with a bit of an ethical dilemma given our current state of practice. For projects, we primarily are forced to use a concentration-based framework, and we don't really consider duration. And we're aware that these limits are likely or very possibly are going to be, we're not going to achieve these concentration-based targets all the time. And clients expect us to move forward with projects, even though we don't really have an alternative right now. And so knowing that, we're forced to essentially be faced with possibly violating conditions of our permitting without any way to solve that issue. And this results in some unmitigated liability for these projects, because right now we're kind of basing our interactions with regulators and the way we conduct ourselves under sort of a good faith approach, where the regulators know that we're trying to do our best, and we know the contractors are trying to do their best, and there isn't a whole lot of enforcement right now, and so we don't really see any precedent as far as that goes. But future changes could have profound impacts on how we do these projects in the future. And another important aspect of this is that there's potential for the optics of the profession to be impacted by this. There's a large and growing database of projects that are documented to violate their permits. They're documenting exceedances for that's open to scrutiny. And regardless of why this is happening, ultimately engineers are signing off on these projects that they know are going to violate these regulatory prescribed limits. And now I want to make it very, very clear that I'm not implying any negligence or any improper decisions. As I mentioned before, there's a distinction between prescribed limits and actual risk to the ecosystem. And so what I'm trying to communicate here is that the framework is not conducive to making optimum economic and environmental decisions as it stands, and that could pose problems in the future. And the root cause for a lot of this is a disconnect between engineering and ecosystems and the way that we design projects and how we understand management of them. And so generally what happens is we design the project, we give it to qualified aquatics professionals to design the risk management. They don't necessarily understand the constraints or the design for the project. And as a result, the mitigation measures may not reflect the sort of pragmatic risk management approaches for a given design or construction approach. And a lot of the times what results in that is budgets going through the roof because we didn't understand that we were going to have to mitigate suspended sediment in a certain way. So what can we do about all of this? And what I'm going to do is make a case for a duration-based suspended sediment management framework that is being implemented under a few specific cases right now that the regulators are approving. And so this is something that can be done in addition to a few other suggestions that I'm going to provide for how we manage these projects moving forward. So to do this, I want to illustrate this concept with a very simple case of constructing a new gravel bed channel. So we're going to simplify things saying that we absolutely will have a sediment release, which is most of the times the case. And the flow is not going to be sufficient in how this is done to cause erosion of the channel. So we only have a superficial layer of fines on the disturbed stream bed that is capable of being entrained into flow. And this looks something like what I'm envisioning here. So this was a project done a couple of years ago and on 3 Point Creek, and the excavator you see near the bottom of the screen is just finished opening up the channel. And now this poses a question when we are talking about exposure risk is how is this done to minimize exposure risk? Do we open up this channel quickly or do we open it up slowly? If it's open quickly, we're going to have a short and intense release. If we open it up slowly, it'll be much less intense over a longer period of time. So the short answer to this question is it's likely going to be a comparable amount of sediment released, so exposure risk is likely to be similar. Now, existing literature doesn't really help too much with the analysis of dynamic releases, but what we can say is there's no evidence to support one approach having more or less risk than the other. So that's, depending on construction, we should be doing this however the contractor feels is easiest to get this thing open, and it doesn't really matter how that's done. Now, there isn't a whole lot of nuance to that answer, but we can sort of flesh this out a little bit more by looking at it in a mathematical sense. So total mass is going to be equal to concentration times duration times discharge. And we can say that total mass and discharge are going to be constant between the two approaches. We're not changing anything about the characteristics of the channel or the amount of flow going through the river. So the duration to wash out the channel is going to be controlled by our decision of opening slow or quick. And as a result, concentration becomes a function of duration. And again, that's an oversimplification, but it is important to illustrate this concept of that our concentration is governed by how we interact with this this channel we're opening up. If we open it up fast, high concentration. If we open it up slow, low concentration. So if we put that into our equation, we have exposure risk being a function of duration. Now, we can generalize this, and we can say that the quicker slow opening of the channel is really reflective or representative of construction production rate. And so production rate of a project will impact the intensity of a release. So what we can say is that total mass of entrained sediment and production rate are two components of a project that we can actually manage. Concentration can't be directly managed because it's highly variable. We can't really predict how much concentration is going to be present during activities. Site characteristics are too complex to evaluate that. But given a project, we can potentially reduce or minimize our exposure risk if we focus on total mass and production rate of construction. So how do we minimize total mass? Well, we can consider more pragmatic design. So if you have different design options, maybe choosing the one that minimizes construction footprint. And also balancing the expected scope and duration of the required scope of construction with the scope and duration required to install sediment control measures. So for large projects like Harvey Passage upgrades or something that's going to take multiple months or multiple years, it's likely that extensive sediment control measures are going to be the proper approach for that project, because the protection from reducing sediment is going to be very important over a long period of time. And again, that order of magnitude analysis, once you're already at a large duration, adding a little bit more duration on isn't going to change the exposure risk very much. Whereas with a small project that can be gotten completed in a very short period of time, we may benefit from prioritizing duration over concentration. And this nuanced approach of figuring out what approaches work well with sort of these medium-sized projects is sort of where my research is focused on, trying to determine exactly what that threshold is and developing best management practices for complex projects that might have a less clear answer to those questions. So now the other component is production rate. And so how do we manage production rate? And that comes down to what I'm proposing is a duration-based compliance framework that I'm working with the government and the city of Calgary on currently to try and implement more widely. So to come up with this framework, we consider the well-established risk tolerance that's proposed in the CCME guidelines of a severity of ill effect of 0.4. And we can select concentration duration pairs that equal that risk tolerance. So on the right side on the table there, you see concentration duration pairs that correspond to the same exposure risk as 25 milligrams per liter over 24 hours. So what we can do at this table is, given the concentration that we're observing on site, given characteristics in the project, the activities, the construction activities, we're going to see an inherent concentration resulting from that. And given that average concentration, we can work for a certain number of hours in the day. And so, for example, if we were observing an average of 50 milligrams per liter, we would be able to work for a maximum of 10 hours in the day. And So that sort of incorporates both concentration and duration. However, it puts the focus on the managing off of duration. And so what this does is it provides a lot of agency to the contractor to manage their own environmental risk. If they run into a situation where they hit an area of that's full of silt, they can either decide to keep going with a high concentration being released and only work for a few hours. Say maybe it's a short section, and getting through that section would only take 15 minutes if they just push through, and they might do that and then decide to stop work for the day because their daily duration limit is very low. However, they can also decide to refine their construction approaches and maybe try and be a bit more careful if they want to work for longer in the day. But either approach does not result in them having downtime or standby expenses. We don't need to prescribe exceedances because as soon as we reach close to the risk tolerance, we just stop for the day and let the ecosystem recover. So it takes that focus away from concentration, and it facilitates our ability to provide alternative mitigation measures that might not be as costly. If, for example, we have a highly sensitive ecosystem, say we're wanting to work in the restricted activity period, and we may find, given the site conditions, that the installing sediment control measures may be too bulky or otherwise not appropriate. We can still get the work done if we prescribe very, very short duration limits. So maybe you only work for 2 or 3 hours in the day, but the project can still go forward in an environmentally acceptable manner. So ultimately what this does is it lowers, it can create a connection between duration and cost, because if we don't have the downtime, if we don't have the standby, lower duration does correlate to lower costs. But it also, if we're looking at the total amount of interactions with the ecosystem, it may also correspond to lower environmental risk. So this is one unique area where the economic and environmental considerations and outcomes may go hand in hand. And managing duration is a lot more, it's a lot more directly tied to environmental risk or exposure risk than trying to manage concentration, because managing concentration has a cost of increasing duration. So as I said, AEP is currently considering this on a case-by-case basis. A lot of the justification I found that they've used to allow for higher risk projects to incorporate this is based on the fact that the research is getting done to better understand this for possibly more widespread adoption of this framework. There is more study that's needed to verify that this is going to work for all projects, especially high risk projects. It has the potential for certain projects that have high releases to potentially halt them from doing construction within an hour of starting construction, hypothetically, and then you might not be able to get enough production using this approach. So some of those high risk activities do require a lot more scrutiny before we can say, yes, this is a good approach for all projects. And on the flip side, small scale projects where the scope of putting sediment control measures in, where that scope is very similar to the size of scope for the actual project, those are very low risk candidates that I would encourage engineers to try and adopt into their projects. They're very low risk projects. If it's a project that's only got a few days up to a week and the stream bed substrate isn't overly fine, those projects are great for this type of approach. So currently, where this research is going is I'm about a few months away from publishing a update to the existing exposure models using sort of a probabilistic framework, so we can better improve the suspended sediment risk assessments and management, trying to better understand that relationship between concentration and duration. And from there, I'm going to use those to analyze a bunch of turbidity data on the Bow River and various tributaries around to better characterize the releases from these projects and the expected exposure risk from common activities to compare which type of approach to a project is best given its site characteristics and the scope of work. And so for that analysis, if anyone does have any data that would be accessible to me for inclusion in that analysis, that the more data I have, the better that analysis can be. And with that, I just want to thank a few organizations that have been helpful through this research, whether it be from funding or other in-kind support or help with my research. As I said, I'm working with the City of Calgary projects. Hopefully that really makes an impact on how we can move forward with these projects. I had funding from NSERC. Wood, I've been working closely with them on a lot of these projects. The Bow River Trout Foundation has been very supportive and helped me do a lot of the experimental work that I did. And Airborne Engineering has been working, I've been working closely with. They have a really strong group of capable drone surveying as well as drone manufacturing capabilities. So that has been really integral into helping me document and understand these plumes. Those photos, aerial photos that you saw were from Airborne Engineering, and they've been a huge help in a lot of that work. So yeah, I think that's about it. I think we can turn to some questions if anyone has any questions.
So there is one question. For your pilot project, what was the reason that the no isolation method was less harmful than the isolation method? That was that the installation themselves had a sediment impact, or was due to effect upon concentration and duration, or another mechanism?
So the reason for the no isolation method being less harmful is that so I guess the motivation for doing that sort of experiment was to answer a very simple question that was does concentration always correlate with exposure risk? We know the models are there that say otherwise, but I wanted a demonstration of that so we can say that given, at least with small scale projects, we can have a physical example of where a isolated project is going to have a higher risk than a non-isolated project, which was very important to demonstrate because most of the all of the existing guidelines and management is requesting sediment control measures. So that was essentially showing that we could have less sediment released and a lower exposure risk because the scope of putting sediment control measures in was so much larger than the works themselves.
We have another question. How do we can approach the duration if work is happening repeatedly over a period? If we were working 10 hours a day, every day for a week, then I assume 50 milligrams a liter wouldn't still be an acceptable concentration.
That's actually a really good question, and it's a point of there's several assumptions that need to be made for these projects, and there isn't good literature to support, like I mentioned, to support dynamic release analysis. So one aspect of that is recovery rates. Once the exposure is completed, how long does it take for the ecosystem to recover? And there's a lot of different ways that could be answered, but the fundamental assumption that we're making with either the current framework or the framework that I'm proposing, a duration-based framework, is that that an overnight rest period is sufficient to essentially reset the ecosystem to fully recover. Now, that hasn't been tested. The existing guidelines suggest that if we keep it to that level of the SEV score of 5.4, that it'll be quickly recoverable, which would be interpreted as overnight would be more than enough to recover. However, if you look at the full scope of projects and what needs to be done, if we were to not consider that, we would likely run into a problem where if we have a 3-week-long period, we would likely run into problems and discrepancies with what is an acceptable spike, what is an acceptable average concentration, what is an acceptable sort of intermittent period. There's all sorts of questions that come up if we don't make that assumption, and none of the existing literature supports that isn't an acceptable assumption. But there's definitely a lot more work that needs to be done to better understand those effect dynamics like rest periods. So for now, that's the best that we can do is use that assumption that an overnight rest period is suitable.
We just have another question. Monitoring guidelines vary with regard to TSS sampling frequency, i.e. Alberta Transportation recommend every hours when in stream and every 3 hours within isolation. Other projects require customized monitoring plans. Is there a preferential sampling frequency or constant sampling logger versus manual sampling when you are using these impact determinations?
Yeah, that's a really good question too. It's something that I'm working on. We're actually working on with the city on developing a system for allowing for continuous sampling that's uploaded through a telemetry system, so that we can get the contractor up to date on their turbidity, their concentration and duration very quickly. The sampling frequency, I'd say the best sampling frequency is the most frequent that you can possibly make it. And the reason is because we want to be able to document the spikes and declines and drops in the plumes as much as possible, because the duration of exposure or the average concentration over a certain duration is very much tied to what that exposure actually looks like. So if we're omitting the peaks of the spikes, our average might go down a bit. If we're omitting some of the valleys in the concentration profile, we may be expected, or we might be showing higher concentrations than we actually are. So I would say what I've sort of come to is sort of 15-minute intervals are sort of a good compromise when taking manual measurements if you can't get continuous, say 1 minute or 5 minute intervals. 15 minutes will give you about an error no more than about 1% on your exposure risk. And so even if your concentration doubled and you missed that through a 15-minute period, your exposure risk would only go up by about 1%, depending on where you're at. So that's kind of a minimum frequency that I would suggest for these. But the sampling methods are still, there's still work to be done to improve sampling methods. So I would say it's definitely definitely improvements to be made there to get a more comprehensive framework for the monitoring.
Okay, we have another question. Are you sampling at only one transect for this 15 minutes interval?
So I would suggest that it's better to sample at one transect at a representative location. Like I usually suggest 10 river widths downstream. It's far enough downstream that you get outside of the sort of initial mixing area, and allow the plume to develop a bit to get some characteristics. And also there's some literature and guidelines related to general wastewater effluents that suggests that compliance be evaluated at 10 river widths downstream. And the reason why it's important to monitor just at one transect, or why that's sufficient, is that the plume's moving downstream, and we really need to characterize it as in as much detail as possible at a given cross section. If we're jumping between areas, we could be missing a spike in the concentration. And we know that downstream we are going to be just seeing a lower diluted plume. So it's going to be wider, but it's going to be less concentration. So I find that getting a high resolution at one transect is sufficient. And further to that, what I have found, again, because of this sort of logarithmic relationship, is that as long as we're close to the high, sort of near the peak concentration within that transect, we can get a very accurate representation of the exposure risk. So even as much as monitoring a single location is usually sufficient, as long as the plume characteristics aren't changing. If you have a giant spur that's being made and going to completely change the hydraulics, and your plume's going to be moving locations substantially, then obviously you need to be reevaluating where that location is of highest concentration. But I think this focus, there is a lot of focus on trying to characterize plumes in a lot of detail by monitoring a lot of different locations. That can be counterproductive if it's at a cost of resolution at one specific location.
So this is the end of the questions. Greg, is there any more questions? Greg's email is on the presentation there. If you have any further questions, feel free to ask him. Greg, thank you very much for spending the time to do that presentation. It was very interesting. And thank you very much, everybody, for attending the presentation. And that concludes the Lunch and Learn. Thank you.
Great. Thank you very much for everyone attending. And yeah, I'm happy to answer any further questions. Either give me a call or send me an email, or if anyone has any interesting projects that could be worthwhile to evaluate for my research, I'm happy to take a look at anything that any interesting projects. Thank you very much.
Thank you.